estimating quantities and scientific notation. These were the notes and lessons that were covered in class on Thursday, August 28th, and Friday, August 29th. Estimating quantities. We can use powers of 10 to estimate and compare really large and really small quantities. We're going to fill out the tables to represent the actual values of large and small powers of 10. Anything to the 0 power is 1. Anything to the first power is itself. 10 squared we know is 100. 10 cubed is 1,000. 10 to the 4th is 10,000. 10 to the 5th, 100,000. 10 to the 6th, 1 million. 10 to the 7th, 10 million. When we were studying integer exponents on Monday the 24th and Tuesday the 25th, we also looked at negative integers as exponents. Still, anything to the 0 power is 1. 10 to the negative first, as an integer exponent, we would say was 1/10. For estimating quantities, we're looking at the decimal equivalent. Same thing here. 10 to the negative second is 100th. 10 to the negative third is 1,000th. 10 to the negative fourth is 10,000th. 10 to the negative fifth is 100,000th. 10 to the negative 6 is 1,000,000th. And 10 to the negative 7th is 10 million, sorry. So to estimate numbers using using a power of 10 and rounding the value, we're going to rewrite it as a single digit times a power of 10. For example, we estimate 9,450 as 9,000, okay, because the 4 tells the 9 to stay, or we say 9 times 10 to the 3rd power. Likewise, we estimate 879 millionths. The 7 tells the 8 to go up, so 9 10,000ths, or 9 times 10 to the negative 4. Because there are 4 places, 1, 2, 3, 4 to move, or 1, 2, 3. Okay, so the exponent is about moves to make. All right, let's do a few of these examples together. 720,432. The 2 tells the 7 to stay. So 700,000 is 7 times 10 to the 5th power. 1,923,000. The 9 tells the 1 to go up. So 2 million, or 2 times 10 to the 6th power. 12,678,200. The 2 tells the 1 to stay for 10 million, or 1 times 10 to the 7th power. When the numbers are really small, we do it the exact same way. We let the second non-zero digit determine how we estimate the first one. The 4 tells the 2 to stay. So 2 thousandths, or 2 times 10 to the negative third. The 6 tells the 5 to go up. For 6 millionths, or 6 times 10 to the negative 6. $878 10 millionths. The 7 tells the 8 to go up. And then we write that as 9 times 10 to the negative 5th. Notice how all of these numbers that started out larger than 1 all ended up with positive exponents. And all of these numbers that started out as decimal values less than 1 ended with negative exponents. We're going to take that concept and apply it to word problems. In 2015, the world population was about 7,390,000. The population of the country Rhett lived in was about 5,926,000. Approximately how many times greater was the population of the world than the country that Rhett lived in? So these are the two values we're using. We're approximately how many times greater. So the population of the world as a power of 10 is 7 times 10 to the 9th. The population of Rhett's country would be 6 times 10 to the 6th. How many times greater? This question implies division. And like it says in the instructions, we're estimating the following problems using powers of 10 and our knowledge of exponent laws. When we're dividing powers, we keep the base and subtract the exponents. 9 minus 6 is 3. Likewise, the diameter of a grain of sand measured 46 10,000ths inches, while the diameter of a dust particle measured about 500 thousandths inches. How many times larger is the diameter of the grain of sand, they mentioned that one first, than the dust particle? So the grain of sand will be 5 times 10 to the negative 3rd. Okay, that's this number here. The dust particle will be 5 times 10 to the negative 5th. How many times greater? Again, the implication of division in the question. We are going to keep the base and subtract the exponents. Be careful here. Negative 3 minus negative 5. Those two negatives merge to create negative 3 plus 5 for an answer of 2. A small town in Texas started with a population of 1,200 people about 50 years ago. Now the town has experienced significant growth and is about 1,320,500 people. Approximately how many times larger is the current population, they mentioned that first, than the town was 50 years ago? So we're going to estimate here. 50 years ago will be 1 times 10 to the 3rd. Current population will be 1 times 10 to the 6th. We have to carefully read the question. Approximately how many times larger is the current population, so that'll be first in our division setup, than the population 50 years ago. 10 to the 6th divided by 10 to the 3rd for 10 to the 3rd. And that is estimating quantities. We have to be really careful to be sure we read the difference in the instructions. These instructions say estimate. At that point, that's when we do our estimations. However, the next lesson is scientific notation. And in scientific notation, we no longer estimate. Okay, so scientific notation is a shorthand way of writing really large or really small numbers. Scientific notation is written as a product of two numbers. The first number must be between 1 and 9, and the second number must be a power of 10. So we're going to create numbers in scientific notation by creating a number that is between 1 and 9 by moving the decimal. We're going to count the number of times that you move the decimal, and that will be your exponent. If the number is greater than 1, like I mentioned before, the exponent will be positive. And if the number is less than 1, the exponent will be negative. So before, in estimating, we would have let the 8 tell the 2 to go up, and we would have called this 2 million. In scientific notation, we're no longer rounding. We take the first non-zero digit and put the decimal right behind it. We keep all other non-zero digits. We're going to multiply by a power of 10. The power is determined by the number of moves it takes to move the decimal from where we put it back to where it goes. 1, 2, 3, 4, 5, 6. 10 to the 6th power. Likewise, in number 2, convert this number to scientific notation. 42,000. 4 2/10 times 10 to the 4th. Again, we put the decimal between the 4 and the 2, and we need 3 more places. So those are the 4 total moves that we took, and that's why it's 4. When the numbers are small, same idea. Put the decimal behind the first non-zero digit. We're going to multiply by a power of 10. We put the decimal here. It takes 1, 2, 3 moves to get the decimal where it needs to be. And this number started out as a decimal number less than 1, so this is -3. Number 4, convert this number. So 1, you can say 1 0/10. It's not necessary, but you can. 1, 2, 3, 4, 5, -5. Okay? We can also convert numbers from scientific back into standard form by moving the decimal the same number of places as the exponent. Okay? The exponent is in charge. If the exponent is positive, move the decimal to the right in order to make the number larger. Okay? Add zeros as placeholders if needed. If the exponent is negative, move the decimal to the left in order to make the number smaller. And again, add zeros as placeholders if necessary. So we're going to convert these numbers from scientific notation into standard notation. So we're going to pick up our decimal. We're going to look at our exponent. It's a +7. Positive, move right. 1, 2, 3, 4, 5, 6, 7. And as the student said in class, put eggs in your basket. All those open spaces get zeros. For 78,300,000. Likewise, convert this number to standard notation. Pick up the decimal. Obey the exponent. It's +4. 1, 2, 3, 4. Open spaces get zeros for 25,000. It also works with taking numbers into really small numbers. We're still going to convert to standard notation. I'm still going to pick up the decimal, and I'm still going to obey the exponent. This time it's negative. When the exponent is negative, move left. 1, 2, 3, 4, 5, 6. Open spaces get zeros. Okay, same thing works here. 3 times 10 to the negative third. Pick up the decimal. Obey the exponent. Negative 3, 1, 2, 3. Okay, so this table has us going back and forth between standard and scientific, or scientific to standard. Again, make that first number between 1 and 9. Always a power of 10, number of moves it takes. Okay, pick up the decimal, obey the exponent. Decimal, 1 digit, times 10, number of moves. Pick up the decimal, obey the exponent. And one more, create a number between 1 and 9, times 10, number of moves. And that is scientific notation.